what we'll talk about now is we'll start getting into some of the more kind of complicated new topics. So the first thing that we'll talk about is, if you remember before, we were talking about how we've got the protons and the neutrons in the nucleus, and how we were keeping them together, weren't we?
Mm-hmm.
Because, like we said, protons, they've got this really strong repulsive force because they're all positive charges. So then we have the neutrons to spread them out, but that alone isn't enough. Okay? What force do we have then that keeps a nucleus stuck together?
A
What do we
strong
call that?
nuclear force.
Yeah, really good. So the strong nuclear force. And what do you know about that? Do you know anything about its range, maybe?
Um,
About how it works?
I think it's um repulsive between, is it 0.5 to 1 femtometers, like in that kind of range, and then up
Mm,
until I think it's 3 femtometers, it's
yeah,
attractive, and then after that, it doesn't do anything, I don't think.
yeah, really good. So if we, I'll do a graph of it, for example. So let's say we had, so I'll say this is attractive and this is repulsive. Okay.
Mm-hmm.
So when we have normally, let's think about the charges of the protons. So the electrostatic forces of repulsion, they go a bit like this, don't they?
Mm-hmm.
In terms of with increasing distance. They they're biggest there, but then they kind of slowly decrease over time. Okay. Then, like you said, and it's really good that you know the numbers, because in questions about the strong nuclear force, they'll often ask about what's the range, things like that. Okay. So up to 0.5, then it's incredibly repulsive. And why is that? Do you know?
I'm not sure I do know actually.
So let's think about it, for example. If it was attractive below 0.5 femtometers, it'd keep on pulling them together, wouldn't it?
Mm-hmm.
And then you get the opposite effect. So rather than everything pushing itself apart
Mm.
and breaking apart, everything would be attracted to each other too much, and then they'd all just kind of crash in on each other, wouldn't
Yeah.
they? We need to keep we need to keep some kind of spacing between them. So what this does is it keeps them all around about half a femtometer apart, but then any bigger than that, it starts to pull them together. And if you compare the magnitude of the attractive force to the repulsive force from the electrostatic parts, you'll see that it's much greater. Yeah.
Mm-hmm.
So the reason why, just remember that, is because it's repulsive less than 0.5 in order to keep them apart so it doesn't just crush in on itself. But between 0.5 and 3, it's very attractive to overcome the repulsive forces. Yeah. And then any bigger than that, they're too far apart and it can't really do anything. Okay. And so, which types of particles does this strong nuclear force act on? Do you know?
Well, in the nucleus, it's the neutrons.
The neutrons, yeah,
Need to,
and the
yeah, on the to act to keep the protons together.
mhm, yeah, Exactly. So it's the protons and the neutrons, isn't it? And you might, like I say, I'm not. All the names sound so similar, so I'm not expecting you to kind of know it all straight away. But do you know what we call those? The protons, neutrons, what type of particle they are?
Hadrons?
Yeah, really good. Really good. Okay. So, as we'll see in a bit, only hadrons can undergo the strong nuclear force. Okay. So then, if an interaction involves any non-hadrons, it cannot be the strong nuclear force. Okay. So, and it's not really important for now, but when we come on to like the conservation laws, whatnot, and equations, it's a bit more important.